again, double integrals and do some more computations. And then we're going to have a discussion session over here, the one on Tuesday. So the quiz is over the whole semester. Okay? And it's graded on completion, as I told you, by email. So that means that if you show up and you take the test and you fill up all of the answers, that's it. You're good to go. I said like 100. So that removes hopefully the pressure of practicing. And that's going to be also an awesome practice for the final. And then what's going to come up after that is the calculus bowl on Friday. So you just have to remember to bring the clipper. That's also going to be an extra practice for the final exam. Make sure that you notice which one is your section. The final exam is on Monday. Okay, Monday the 30 hours. Okay, and now directors over here. Any questions? Yeah.
Okay, when is the midterm grade going to be posted with the quiz?
Before the weekend. Yeah. So I do have the grades, and I'm just putting them all together so that we can have an adjusted grading that's going to be on Quest. So what you're going to see on Quest is it. That's it. It's already kind of taken care of the quiz adjustment. What do I want? Okay. Okay. So first question that we've got for today. Oh yeah. Sorry.
Which exam are we? The 13th, right?
Yeah.
Yeah.
What did you ask me?
I asked you what date we have.
What day is the exam? Monday. The final exam? Yeah. Okay, so one thing that I want to go over, we talked about what what fx is, what fy is, and we're getting into the double derivatives. So we've got a point, let's say 1, 2. Now we've got 3 dimensions, and the question for you is, what is the geometrical meaning of fx at that point? What does it represent? Yeah.
Derivative with respect to x.
That's the derivative. That's the meaning of the symbol. Very good. So that's the partial derivative of the function f with respect to the variable x, and that's going to be later evaluated at the point 1, 2. Geometrically, how do I actually look at it? Yeah.
Slope of the tangent line point 1, 2 as x changes with y.
Pardon? As the last part.
X changes with y.
As x changes with y,
As y is constant.
y is constant. Okay, I want to understand that. Did everybody hear what Sean said? It's the slope of the changing method. Write it down. Don't write this. This is just a work in progress. So we get some ideas. That's going to be the slope of the tangent line at the point 1, 2. That's it? Okay. So let's try to understand how things work actually in 3 dimensions. And we've got this picture over here. So for example, I'm going to pick this point right here. So would you say that the derivative, remember this is going to be x, this is going to be y, and z is over here. Would you say that fx is positive or negative at this point? Let's call it capital P. Is that negative? Negative over here? Why negative?
Because it's flowing away from the x in the x direction. I don't know. It's just that's what it looks like.
What does it mean by flowing away? Because, for example, what about this point over here?
That's positive.
That's positive. So what do you mean by flowing away? Because that also kind of flows away from x.
I don't know.
Can we help them? Yeah. Yeah.
As the slope goes in the x direction, it's decreasing the output.
Yeah. So if I keep going, if you think about that point, that's the end, and the end is kind of walking on the saddle, and it's going in a positive direction. So you have to kind of follow the arrow, follow the direction of the x, and then what happens over here is that I'm going down. And over here. This one is a tangent line to my knuckle. Is that true? Hunter, what do you think? Everybody agrees? That's a tangent line? What about this one? Is this a tangent line, Hunter? This one? So how many tangent lines do I have to a point on a surface? I've got infinitely many. So that's why it's very important. Not just say to the slope of the tangent line at 1, 2, but we need to add something like in which direction. So we can say, well, that's the slope of the tangent line at 1, 2 in the x direction. And that's what Sean mentioned at the very beginning. You're going to keep the y constant. And then you're going to see how essentially what the graph looks like if you're taking that surface and you're going to cut it with a vertical plane in the, you're going to see the picture in the x, z plane. Okay, so that is what fx is, like the slope of the tangent of a tangent line. Fy is going to be exactly the same thing, but I'm going in the other direction. What is fxx at 1, 2? That's the concavity with respect to x. Again, we're always talking about direction here. So that's going to be the concavity in x direction. For example, over here, let's take this point B. Does it have a positive fxx or a negative fxx or 0?
Positive.
Positive what? What am I looking at to decide whether it's positive, negative, or 0?
Concavity.
I'm looking for the concavity, but again, it's the concavity in the x direction. So you just look at this line over here as a mesh, and you look if it's a concave up or a concave down. Now, the interesting thing about this point is that the fxx is actually positive, and what happens to the fyy? The fyy is negative. So in 2 dimensions, you can actually have like a very like a saddle point. What it means is that it goes down in one direction, it goes up in the other direction. So these things can happen in 3 dimensions. Whereas in just 1 dimension, all you have is just going up or down. That's it. So but here the direction in which you're doing things will really matter. Alright, so now what I want you to do, guys, is think about this other object. fxy. 1, 2. What is this? So get together with a neighbor and start picturing this fxy. And also, of course, we do have the other one, which is fyx. Because here I'm taking 2 derivatives, and if I've got x and y to play with, I could take 2 derivatives with respect to the same variable or mix and match. There's no function. The function is the surface. But just try to understand what is that it measures.
So I guess what x sub xy would mean is like, what does the slope with respect to x do when I change y? You can see one of these things. So if I okay, so if there's slope with respect to x, what happens when I change y? Because the slope seems to upward as I go. see how the thing is. Yeah. So it seems to get steeper and steeper. It's like, well, so that would imply what?
Okay, then F of X is
So as I increase y, the slope.
So is it the concavity of X and Y direction?
Kind of. It's not as simple as it really depends on what the slope is.
So what am I doing to get fxy? What?
So we're doing the f1. Okay, so if we look at f sub y, it's doing this, and then I need to modify x and see what it does. So if I decrease it does this. And if I increase x, it's kind of.
So why is constant x? So it's saying, alright, if I start walking through x,
You see it kind of like the shape it's swings in. So
we said that would be what? Negative?
So after that, you just take that.
Yeah,
So this is like the intuitive moving. So like if I wanted to see if it was positive,
we're going like that way. We're like walking that way. You're going like down here. Am I looking wrong?
so what happens to the slope as I increase like y? So it's positive.
Oh, sorry. Oh, yeah, then you're right. Yeah, in that case, it's positive. So now you want to know, how is that going to change?
So the slope is increasing.
Are you going to be going like more uphill or less uphill if you start? So that's, I mean, it's hard for me to tell.
So it's like, you say it's like direct.
Yeah, they're related, but it's not as simple as terms like concavity.
What would you say that fx, the sign of fxy?
Contort your hand in weird ways.
Yeah, you're getting shouted.
But the reason actually used to it, that will come to
Not necessarily. Because, I mean, the concavity is positive, right? I mean, for in the x-ray.
In order to
Yeah, it should be like changes. The x-ray should be but if you start moving in the y direction, they get shallower. So you sort of see that as you start moving like out or backward,
I don't understand this.
it's not supportive. Yeah, if you're thinking about this as like a hill, so it's not a hill. It's less uphill. Yeah. Yeah. So you actually have a sign of that effect. So let's think about what happens at that other point. So the first point, right? So there the derivative is actually negative, right? And then what happens if you start going in the y direction? It's sort of, I mean, it's sort of concavity, but it's not in like, it's not all the way direction.
She says, like, what is it?
So when I think of concavity, I think, what's happening in my, like,
knowing
because the notion of concavity is more complicated.
So for instance, let's say I had
Specify all the directions.
so then I went with the y derivative, so exactly using y derivative. Looks like now it's kind of like it's doing this.
Not necessarily.
Then I would see that it's getting steeper still, but it's
Not necessarily.
it's getting more negative, so to speak.
Let's see.
So you have to be really happy with this process of, okay, what is the next derivative?
Yeah, I'm trying to find a point out
I just printed all this out because I have no idea what we're doing. I get this,
Yeah, so as I increase one,
but that's not what I
Why or
Okay, don't understand what the point of this is.
It's hard to visualize. Yeah, what's happening to the lines in the y direction?
Because one of them, like this side's becoming more and more
Yeah.
because it's the metal is like so it takes out electrons from the metal and goes away and when it's an iron filter. So to counteract that, the software this is going to be because this is becoming less powerful. So it's going to be
Start walking in the y direction, you're going down.
just going to go away from it. Because this is taking in the positive ions and making them move.
So it has to get. Okay.
You're moving like towards it.
So,
See how like on the y axis?
and negative
So what would happen if you didn't have that?
it
It just wouldn't work?
really quickly.
What about
It's actually
But I don't know, let's see.
that's just what the software just
You
made.
go kind of along the y-axis. You start to start walking in the y direction.
look at something a different way?
Yeah.
I didn't say I was like really, like I think everybody
It's somewhat hard to see, but ideas really about how the source and tangent lines are being moved
So this is just really like
It takes some practice, but
Yeah. Don't imagine. So like whenever we do why?
that's a really, really good question. So, do you think there? Let's see if we can figure out anything about them. So, how are the
So what
of the
happens?
x tangent lines
Is there ever a time when
moving
you're
in the
not
y direction at that point? Are they getting more shallow?
It's like Z.
Yeah, so it'll be as you start moving in the y direction, it looks like they are sort of going up a little bit. So it
There's
looks
like X and Y
they're
or
positive there. What if you did it in the opposite direction? What if you looked at the tangent lines in the y direction
So
and then
X and Y
started
like
moving a little bit in the x direction?
so if you were to graph X
So
and
they're
Y
also
together, it just be
like so both of these guys are negative, so maybe
they have no interaction.
so that's a really good question. Like, does it look like there's some sort of relationship between fxy and one and fyx?
It's like an introduction to
What do you think it is? Any idea?
you don't have to bring by it. But I'm taking that.
It's a good thing to think about. I would really encourage you to ask that question a little bit. Or you,
Okay, so I found a very good thing. Okay, so I just want to with this side and we heard a very good things. For example, Harrison has a beautiful idea and essentially we're talking about the relationship between fx taking a dy on top of that, what does a derivative represent? What does it measure? It's a rate of change, and that's one of the most important things I want you to remember from the whole course, from the whole calculus, okay, curriculum. So it's a rate of change. It's a rate of change of what? Of? So we've got fx over here, that's what Sean was considering over here. And then we're taking a derivative with respect to y, which is what? The rate of change of, with respect to y, of what? Hmm?
Of that tangent line.
Oh my goodness, yes sir. Okay, perfect, perfect. So what we have over there is, I got distracted by laughing over here.
I'm sorry.
Is that funny though?
It's like inside joke.
Okay, then you have to, when the cameras are off.
Yeah.
Okay, perfect. All right, so we've got this derivative over here. Okay, and that's going to be f of x. Now, if I take a derivative with respect to y, you told me it's a rate of change. So it's a rate of change of the slope. So we're letting the slope change. Okay, and so we're changing the slope along the y, and we see how that changes, essentially. So let's do an example over there. So at this point, 1, 2. Okay, so if I take the derivative with respect to x, I get this object over here. Okay, and what I do is to kind of move a little bit kind of close by, and I just follow the mesh because it's easier. But technically, anytime we're talking about rates of change, we're talking about a limit. Okay, so we don't talk about something happening at a point, we're looking nearby. Okay, so I'm going to do this. I'm going to take this point over here, and I get this derivative, and then I get this derivative, and then I get this derivative. And so what happens is that I start with the derivative at the very back. It's a slope like this. Then I'm going to move a little bit closer to the front, and here's what happens to the slope. Then closer to the front, this is what the slope is. So what happens to the rate of change? Let me do it again, but you have to look at me. This is the very back. Closer to the front, more to the front. What's happening to the slope? It's increasing. Very good. So would that be a positive or negative fxy? It's a positive one. It's increasing. So what is it measuring? The change in slope, like for example, one thing is the rate of change, that is slope of a tangent line, fx. Fxx is called concavity. How can we call fxy? The rate of change of the slope in one word? It's like a circularity type of thing. It's like it's a curly, yes. It's a curly thing. What did you say exactly?
It's a twirly.
Twirly, yes. It's like a curl, whatever. That's exactly what it is. So an fxy measures the twist that you give to the surface. So an fxy is going to tell apart this from this. So when you, it's not very practical. But anyway, like from here, here's everything okay. All of the tangent lines that line up. And then what happens is that you twist them. So you get like some sort of curl, some sort of, yeah, like a twist. Does it make sense to everybody? That is a very important idea. So concavity, slopes, and the twist of the surface. Yeah.
So fxy is the change in the slope of x as you travel along the y direction?
Right. The thing is that actually, it depends on the order in which we do these things. But there's a beautiful theorem which says what? What about fxy and fyx? How do they compare? So what happens is that these two are the same thing. So it doesn't really matter. You're taking the derivative in x first, so you're looking at what happens. You're taking this one slope, and then you let the y change, or you take the slope in the other direction, and then you let the other variable change. So that's the data go without using the fundamental theorem of calculus. So I don't want to see any math in it. I would just want to see a picture.
I know how to do this with math.
Front center, right?
Oh yeah. Oh, I thought that you like.
So basically the answer would be 15 if we computed it, right?
Well, we're not allowed to access.
Okay, so let's investigate. Over here. Oh, look, he already started different reading.
Yeah, I don't know.
Yeah, so he joined what's it called? He joined reading and then so anytime we have a data measurement thing, you want to be right quick, you want to know how reactions. So if you're at 150
Just had this curve. Tell me about this line. How do you know that's right?
I think it depends on what.
I think so, maybe.
It's like a log, but it's the top is not going to be able to
Yeah, that's probably.
Keep your instruction.
Is that the range? Is that the area?
The y-axis.
Oh, wait, no, go down.
That's, you're right, that's the area.
It's got the flat bottom.
I get it all right there.
Because it's like a
Five by zero.
how tall it is right then it goes up, I think it goes up by 5 or minus 6. Because when it was 5, it was 6. What did he represent? Up to 6 or 0. And now our Z is 5. So what is that like?
Yeah. Yeah, the height was
This is half the area, half the area, right?
the same way.
If we took this shape, upside down, it's higher than so I think it would just be
Here, the height is not.
yeah, well, you could do this and you can do this upside down and this
Even though the height right
So what did we draw here?
Yeah, so it's gonna be like yeah, it'd be like a wall.
That's 5
Yeah, it's not sure anymore.
So what is that say? Are you like that's the beginning of the point.
Well, but then yeah, for this whole why is not around? So why you want it? Why am I? Well, I mean, are you?
But is it on rent? Like, are you getting the rent on next rent or the rent? Or are you getting loans or are you getting one? Which is like, because I have the program, there's the requirement of finishing some winter.
So,
How do we know exactly?
5 minus X.
So I can
This kind of.
now, if you're on the seat,
okay.
so you're just gonna change the respect to Y, right? Then you can, then like the text will be taken away. For me, it gave me like the chunk of his money was $7,000. So I don't want to lose that one. I'm just saying that. Look into that.
Okay, how's it going here?
So this is going to affect your GPA that much. I'd rather, like, it'd be better if you did, or if we just use like, capacity on you, and then like, if you make it dean level, like, you know,
Yeah, so why is this like 0?
I don't know.
What is that? What is
I know a bunch of universities.
So if I'm just saying, why do you zero?
got the code here.
Like in the university, yeah. That's probably why I like in other universities, I know
So it's this thing. Anytime something doesn't fit you just move it, like translate it in that direction. So it fills out all the like constant. Each point. So it becomes a this, right? It becomes a lane with that same thing. What's different? I first of all, I just look at the So I just draw that into the machine. And then I'm going to introduce the y. And so I just look at this.
Figure out.
Oh, look at calculating. That's radical. I'm going to just consider that. And I'm going to just
So how can you build this out of a stack? Area, yeah, but you're gonna build it out of a stack of what? Yeah, you're gonna build it out of like a stack of
it's got some depth. Yeah, exactly.
How is this a stack?
And it's not, don't you go to the bar into the y-axis, so it's really like this. We just bonds on the region, and that's how in depth. We're gonna go there. Okay guys, so what does it look like? Yes, so it's a triangular looking pyramid. Yeah, it's called prism. It's not really, a pyramid has got like a pointy thingy. So it's more like a prism. Like in practical terms, what does it look like? We're talking about a rim over here. Anybody with any practical? Half a tenth? Yes, it's a nice one. Yes, cheese. A slice of cheese. Anything else? Okay, I think that really tells us that we are after lunch, because my earlier section, it was all about food. A slice of pizza, a slice of pie, and all of that. Perfect. Okay, so let's try to understand how we draw this. We've got, first of all, in 3 dimensions, we are integrating a function, right? And what's the function? The function is 5 minus x. So that's going to be my z equals to 5 minus x, f of x, y. So the function is 2 variables. All right, so we're going for this picture, which is a 2-dimensional picture at this point. Everybody good with that? Okay, this is a simple straight line. Slope of, what's the slope of that line? -1. It's a slope of -1, and does it have any y? No, it doesn't have any y, and that's the key. So anytime you don't have any y, then what happens is that you take this object, this line, and then it becomes, you just translate it in the y direction. So I'm assuming that this is my y. So essentially, it doesn't depend on one of the variables, so we get like a plane. And remember the rule, the little rule that we discussed the other day. How many variables do we have? 3 variables. How many equations? One equation is just z equals to 5 minus x. So we're left with two different ways of moving around. So we are on a plane, we're not on a line. So that's really important. Okay, so here's a picture. Are you ready? There you go. So that's the slice of cheese. So basically, first we draw the function, I would say. First we're going to draw the function, which is this plane over here that you see. And then I'm going to look at the region, because I'm going to integrate this function over this particular region R, which is just a rectangle, okay, 5 by 3. And so you see the x component is over here, 5, and I've got the 3 over here. So what's the volume here? What's the volume of this thingy? 37.5. So essentially what we do is we can take the area of the rectangle, of the triangle, which is this face over here, and we can use the fact that the function doesn't depend on y to just say, okay, take this area and then multiply by the width. That's really just a formula for the volume of the prism. And so all we are using here is visualizing our functions in 3 dimensions, and we're using basic, like slicing, essentially. And realizing that when we're talking about an integral, a double integral, what we're checking is the volume. We have a double integral just because we have 2 variables like x and y. Okay, so what's the definition of a double integral? Like, what is this integral of a function x, y, dx, dy? How can we make sense of this? What is it? Like formally. What can we do? Well, not too formally. Just if I ask you, for example, how to compute an integral in 1 dimension, a 1-dimensional integral, what would you do? It's the area under the curve, and so how do you approximate it? Yes, we're using rectangles. We're using, remember, Riemann sums. Now we're going to do exactly the same thing over here, and I picked up some pictures from the book, which are really nice. Just describing this idea of Riemann sums, but in 3 dimensions. So you see that essentially our 3-dimensional analog of the rectangle is this thingy, 3-dimensional little stick, or brick, whatever. So that would be, you see, this would be our Riemann sum if we only had 1 dimension. But then if we repeat the same thing with 2 dimensions, like an x and a y, then what we have is this collection of areas, okay? So we've got this little square area over here, and then we're going to take a height, and then we're going to take the area of the base times the height, which is going to be equal to the volume of each of these individual sticks. And then we're going to put them all together. And if we take more and more of these, you see that we're getting a better and better approximation. So this motivates the formula that you saw in the learning module, where we take a limit as n goes to infinity and m goes to infinity, and then we're going to take an n and an m, well, let's say I over here, j from 1 to say n, it doesn't really matter those names. Then we're going to take a representative, say xij, comma, oh my goodness, wait a second, let me just get more space. So I've got f of xij, comma yij, just a representative, delta x, delta y. So what we're doing here is exactly the midpoint rule, okay, from Coq 1. So we're taking a point into that little square area, which is right here. We're going to take a representative, which is just the middle or whatever you want to take. And then eventually we're going to let those go to infinity, which means that I'm going to have so many of those little sticks that it's going to kind of cover up the whole volume. So that's what justifies this 2 summation. So you're going to sum all of those little squares over here. And so you can imagine starting doing a summation in this direction, summing all of these guys, and then we're going to sum them in the other direction. So you start from row 1, and you just sum all of those, and then you move to row 2, you add row 3, add row 4, and all of that. Okay. Any questions, anybody? No questions? Okay, so I'm going to see you on Monday.
decompress, right?
Decompress in the standard tree format.
Yeah.
Oh, did you go for a while?
Yeah.